Right, so in this problem, what we have, oops, so start off by assuming we've got just some random line in the plane, some, like that. And I'm drawing it at an angle just to show that it can. It doesn't matter what line this is. And it says that if you have a small little piece of area here, and if you take that little piece of area and rotate it around the line, oops. Now it's going to make a little volume of some sort, some a little weird shape like that, but it's got a certain amount of volume. And you could ask yourself, how does that volume relate to the original piece of area? We've got this little piece of area there, right? And I claim it, if you think about it, one thing you could do is you could take a pair of scissors and you could just kind of, this is sort of a rubber band of sort. Okay. Just cut it with a pair of scissors, just chop it on one spot and kind of straighten it out. And I claim that dV is going to be the circumference times that area. Does that make sense? And then, of course, now you can compute the circumference because the circumference is going to be 2 pi times that radius, so whatever that distance is. I'm going to call that r. Now, you got to be a little careful because if I call it r, that means it's the distance, it's the radius of that little circle. It's not the polar coordinate r, which is the distance to the origin. So you got to be a little careful with that. So, but otherwise, dV is just 2 pi r dA. So this is the idea that's being suggested with that first sentence of this problem.
Oh, okay.
Yeah, is that cool?
Yeah, this completely did not do that funny problem.
Okay. Yeah, as I've been explaining this here, I've probably said 20 sentences. I've really, expanded and explained and drawn pictures and stuff. And in the statement of the problem, it's one sentence. So in the statement of the problem, it was just very, very compact. So what you'd have to do to make sense out of the way it's written in the statement of the problem is just look very, very carefully, kind of draw your picture as you go through the problem, and very slowly and carefully analyze each little bit. And I think you'd come up with this picture, and you might be able to make sense out of it.
So now we know that 2 pi r is well, at least r is an integrand, right?
Well, not quite. We're not sure what the integrand is yet, but this is a relationship between the volume that's swept out compared to the area that you started with.
Oh, just that the question says right in terms of double integrals.
Yeah. No, we'll get to that. But
we're not finished.
No, we're not finished. No. This is just all I've done here is made sense out of that first sentence.
Oh, okay.
Yeah, that's it. So now the problem says use this idea to write down and compute a double integral representing a certain volume. So now this was an abstraction. Let's talk about the actual specifics of our problem. We got a triangle with certain vertices. And the vertices are at the origin and 1, 0 and 0, 1. So here's our triangle. I'm running out of ink in this pen here. There's our triangle. Yay? Okay. We're going to rotate that around the y-axis. Here's the y-axis, so we're going to rotate that like that. And that sweeps out a certain amount of volume. And yeah, that's right. And you might view this as, we did this in single variable calculus classes. I'm sorry?
Is it a cone?
Yeah, it makes a cone. That's exactly right. But I don't want to draw the picture. I want to just use this idea here to see if we can't make sense out of this. So what we've got, I claim that if you just look one at a time at little bitty pieces of area here, like that, and ask, well, how much volume does that little thing make as you rotate it around? You rotate that around, right? If you add those volumes up, each one of those little things makes a little volume here. If you add up all these little volumes, all of these little volumes, in other words, corresponding to all these little pieces of area, then they'll give you the total volume. In other words, I claim that the total volume is a sum where you're adding up over this whole triangle of these rotated volumes that you get like that. And now we just have to figure out, what does that mean? What are the specifics here? We've got 2 pi r dA, but we've got to figure out specifically what in the world is that. Right? Because up here I never said what r was, other than, well, here it is in the picture, but how do you compute it? So, well, in this picture you've just got to decide and there's what it's supposed to be. It's that distance. That's your r. Does that make sense? And I claim it's x. So all we have then is our volume is a double integral over t of 2 pi x dA. So that's the double integral. Now we're supposed to also compute this. So I've got to rewrite now even further. And this is a triangle, so it doesn't really matter too terribly much which way I do this. So I've got y going from 0 to 1, and then for a given value of y, x goes from 0 to, well, I have to figure out what that is. That is a point on x plus y equals 1, because that's what that line is. And I need to solve for what x is. X is 1 minus y.
Okay.
So then this is a nested interval. So step 1, so the interesting part of this problem is actually the step 1, the phase 1, where you take the problem and you try to use this concept to interpret how this rotated volume turns into, in fact, a double integral. Yeah, and then this part is sort of a straight out of this section conversion, and of course then you calculate. Yeah. Everybody good?